All right, let's see, we have 28 questions on the exam. I showed you the distribution of questions in class. It follows that mostly. That I think I might have added in one additional RC circuits. I think I had 2 listed. I think I put 3 instead of that. What do you want to look at? Yeah, Blair? Yeah. Okay. I think there are about 6 questions that come from OpenStax. And I changed the numbers, but you know, they're the same. But the other questions, they're similar, so it's good practice for you to go through that. Which one? This one? The after 2 time constants? All right, so will this let me write on here? I don't think so. I'm just going to do it right here. So the voltage on a charging capacitor, and that's what I have. I know it's a charging capacitor because it's initially uncharged. And then I'm looking for how does the voltage change. So it starts out with a voltage of 0. And you want to look for those keywords like that. That is uncharged, or that it's charging, or that it's initially initially not in a circuit and then it's added in. But I know that the voltage is equal to V naught times 1 minus e to the minus t over RC. And then if I want to know the percentage of the final voltage that's on this initially uncharged, to do that I just say V over V naught. That'll give me my percentage. You know, I'll need to multiply it times 100 in order to make it into a percent. But then that's going to be equal to 1 minus e to the minus t over RC. But since I'm looking at 2 time constants, then this is going to be equal to 1 minus e to the minus 2 tau over tau. So the tau's just cancel out. Look what I did there. I replaced RC with tau, because that is what tau is. And then I put 2 tau here instead of t, because I'm looking for 2 time constants. Huh? Right. So I'm just setting t. I let t equal to 2 tau. And then that's equal to 0.865, which is 86.5%. Okay? All right. Any other OpenStax while I'm here? Number 5? Yeah, it's hard. Was there a resistor down here? Okay. Oh, yes. So, I'll redraw the figure. Now, so what we have here is first, you charge this capacitor with this battery. So what it's talking about is that I'm not going to give you a circuit that's like this exactly, but you'll need to be able to work this type of problem. But I charge this capacitor with this battery. If I have a 2 microfarad capacitor, this should be 2, not 20, and I'll get 20 microcoulombs on that capacitor. Q is equal to C times V. So I'm going to get 20 microcoulombs. That's 2 times 10 volts, 20 microcoulombs, and then I am discharging it through that 10 ohm resistor. So that's going to look like this. I'll have a capacitor that's 2 microfarads with 20 microcoulombs because I charged it with a 10 volt battery, discharging it through a 10 ohm resistor, and I want to know the current at 4.5 microseconds. What is the current at t equal 4.5 times 10 to the minus 6 seconds? You go to your equation sheet and you look for what is the current for a discharging capacitor. And you'll find that it decays with time. So it's equal to the initial current times e to the minus t over RC. Now, how do you find that initial current? What is the initial current? Well, initially, I'm going to have 10 volts across that capacitor. It's like it still holds that 10 volts from the battery. And so this is going to be equal to 10 volts over 10 ohms. It's all right. Oh, that's the air conditioner. Times e to the minus t over RC. Right, wasn't it a 10-volt battery that was charging it? Yeah. So then I go on, that's 1 amp, e to the minus 4.5 times 10 to the minus 6 seconds, divided by RC. 10 ohms, 20 microfarads. So that's 200 times 10 to the minus 6. Huh? Right, 2, you're right. So this is just going to be 20 times 10 to the minus 6. And then whatever, I don't know what that gives you. E to the minus 4.5 over 20. Your 10 to the minus 6 is canceled out. Oh, is it asking for the charge? Okay, I'm sorry. Yeah, so that's going to be Q is equal to our initial charge times e to the minus t over RC. So that's going to be 20 microcoulombs times that e to the minus 4.5 over 20, where I just canceled these out.
So why would you do 4.5 and not 4.5 to -6?
I did it over here, but yeah, it canceled out because my time constant is 20 microseconds, and my time is 4.5 microseconds. So these two micros, they cancel out. They just divide out.
Right. So on that question, like, how would you know to cancel it? Because, like, I've done it 4.5 times 10 to the minus 6 over 20, and that gives you 20, which you put on the answer. But if you do just 4.5, but if you're just reading it out.
Right. Be careful with this. Usually when we calculate tau, usually the way we usually do them, probably the way you'll see them tomorrow, R is in mega ohms and C is in microcoulombs. Often that's the way it is in RC circuits. And in that case, the mega, which is 10 to the 6, and the micro, which is 10 to the minus 6, they cancel out. Just a second, Marissa. But in this case, that wasn't the case. Here, tau, not T, tau is equal to 10 ohms times 2 microfarads. So my tau is not 20 seconds, it's 20 microseconds. So really, I have to write that, is it called a mantissa? I think it's called a mantissa. That extra bit, because it's microseconds, not seconds. In practice, though, I will give you an RC circuit that has a time constant that's seconds, not microseconds. It just makes the math easier.
So, tau and time are not the same.
No. Tau is your time constant. Tau is a characteristic time for your RC circuit. Remember, to charge a capacitor fully, you have to have 10 time constants passed. Tau is just this characteristic time. We use it to describe exponential functions. But t is the actual time that I want to know, whatever it is that I want to know.
So they're asking you to hold another time for tau.
Right. T, RC is equivalent to tau. Tau is RC. Okay? Marissa?
I got it.
You got it? Awesome. I'm glad I can help. All right?
Number 6, dude.
Sure. Okay, so this one is not difficult, it's just a little quirky. So I want it to travel 1 millimeter in one time constant. The time constant is tau. Tau is equal to RC. It can travel 1 millimeter. T is d over v. right? Meters over meters per second, that gives me time. D is 1 millimeter divided by V, which is 500 meters per second. So this is the time that it can travel 1 millimeter. I set that equal then, whatever this is, I don't know what the value is, but I set it equal to the time constant. Because I'm looking for an RC circuit that will have a time constant that's equivalent to the time that it takes this bullet to travel 1 millimeter. Right, yeah, 1 millimeter. Okay? Oh, not the capacitance, this whole thing. So let's just see it through to the end.
So T just happens to be equal to time, but it's a lot of things. In this problem, it just happens.
In this case, right.
So say it was 2 constant.
Then it would be 2 tau is equal to T. Yeah. Tau is just a characteristic time for the circuit. I think you charge about 67% of your capacitor with tau. Or is it 33? I forget which one of those. It's a characteristic time. You want me to carry it through to the end? Okay. So this T is 2 times 10 to the minus 6 seconds. That's what I want tau to be. And that's equal to R times C, which is 600 times 10 to the minus 6 farads. That was down here. Those cancel. It's 2 over 600 is R. 3.33 times 10 to the minus 3.
So you're putting that into S tau because it says assume 1 millimeters and then 1 RC constant.
Right, because the time for travel this distance is 2 microseconds. That's 2 times 10 to the minus 6. And that's 1 time constant. Okay? Then your 2 millimeters would come in up here. Okay? These are all good questions. You know, a lot of the tests is not really, well, most of the tests is testing your physics knowledge, but it's just reading the problems and thinking about the scenario, that it's not even really the physics. Like this, that's not physics, right? Just reading the problem and figuring out what is the time constant related to. Which y'all are good at. Y'all can do that. Right? Just relax. I think y'all get a little too uptight during the exam. You need to relax. Like, get a good night's sleep tonight. Study, but get a good night's sleep. Go to bed at 8 o'clock. Get a good night's sleep, for goodness sake. I don't sleep enough.
Thank you for your advice.
Okay. What else? You want to look at some old exams? All right. Oh, are there any particular questions about exams? I know some of you come with a big long list of questions. All right. Okay. Oh, this is 101. Don't like that. Okay, there. Okay. Multi-loop circuits. You're going to see 3 or 4 questions on multi-loop circuits. It doesn't take that long. All right, here we go. How y'all feel for multi-loops? your first few questions are going to be kind of like this. You'll see a question. It'll ask you what are the correct equation, which is the correct equation, and then it'll be followed by what is the current in this particular. Yeah.
Direction. If you get a negative number, you just switch the direction that you found it in.
Right. So, for example, on this one, if I want to know the magnitude of I2, first of all, I need to recognize that I want to look at this loop because this branch over here has no resistor in it. And then I would say negative 2I2 plus 4 minus 8 equals 0. Write my loop rule. That started here, went in this direction. I had negative 2I2 because I'm going with the current, plus 4 because I'm going from low to high potential, minus 8 because I'm going from big to little, from high to low potential, and then I'd solve that for I2. And I2 is equal to negative 2. Yes, negative 2. And so that means that even though the current is listed as down, that it should be up, 2 amps upward. If you get it negative, just take the opposite. Yeah, Cassie? Okay, there are 2 directions. And usually on the questions, like on this one, for example, I give you the directions for the current. So I give you these directions for the current, but they're not necessarily correct. Although there's no correct or incorrect, it's just the direction that you choose. But I choose them for you. And then there's another direction that you choose, the direction to travel through the circuit. I say travel. As you write out the loop rule, which direction do you go? Do you go like this or do you go like this? Now you pick that. However, you might also have a question, you will also have a question where I don't give you any directions. I don't see one here. But you have 3 or 4 multi-loops. One of them's like this, where I give you the directions and you have to pick out the right equation, and then you have to calculate a current. But then I give you another circuit that doesn't have any directions on it. And you just pick those directions randomly. And I tell you, okay, pick the current in the 3 ohm resistor or whatever. It doesn't matter. Just pick whatever you want. I don't care. It doesn't matter. There's no reason to pick any direction.
And would the current be down? What would an example of current down be?
If this came out as positive 2, then the current would be in the direction.
Look at the current. So if it's negative, the current is the opposite of what's on the diagram.
That's right.
If it's positive, it's the same as what's on the
That's
diagram.
right. Lizzie, did I answer your question? You sure? All right. You good on that? 4 questions. 3 or 4. I think 4.
So you said there's not going to be one where we have to where we don't know any of the.
No, there will not be one like where you don't know any of the currents. I will give you one of them, and that makes it easier to solve. But there is a question where you have to take a couple steps. So where you have to figure out one current to figure out another current.
Yeah.
But they're still, algebraically, they're relatively simple. There's no substituting equations into one another.
Okay.
Yeah.
If this was like a special case, because I worked it from this way and going this way, and I got negative 4 times. So how,
Yes.
that one's different?
No, no.
No?
So she showed me a circuit where it had, I'll just draw one.
So it's supposed to be negative both ways.
The direction of your current didn't change. The only thing that changed was the direction that you travel through the circuit. Let me just, this isn't the same as what she showed me, but it's similar. She had a circuit that was just a single loop, but with multiple batteries, and the current was in that direction. And she tried writing the loop rule going in this direction, and then writing the loop rule going in that direction. And in both cases, she found the current to be negative. But notice that even though she changed the direction that she travels around the circuit, that the direction of the current doesn't change. And so both ways you should get a negative current because this direction is incorrect. There is no correct or incorrect for these directions. That's just the direction that you're writing your equation.
So what would the direction of the current be?
If you came it to be negative, it would be, it's counterclockwise now, it should be clockwise. Or, I don't know how it's written in that. Usually I do it up or down.
You didn't ask specifically in this problem
Yeah.
the direction was, but I was just wondering if
It
you
would
did.
be clockwise.
Okay.
It came out negative.
Okay.
All right. You're going to have one of these. Y'all okay on these? You know how to identify growth and decay functions? This is a decay, e to the minus t over rc. This is a growth, 1 minus e to the minus t over rc. You won't see any, like, those aren't physical. Don't memorize the order, just remember the shape. I always remember that this thing always goes to 0, this function goes to 0. This thing always goes to 1, this one approaches 1. This function doesn't approach a value, right? It just plummets down to 0. And this is linear, so it doesn't, that's not an exponential curve at all. Yay? Yeah, Mallory? Okay. Any of these jump out at you? Don't be shy. Uh-huh. Okay, so 13, it's a nice problem because it has all of our different applications of the right-hand rule. So here you have to do a couple of things. First, you have to figure out the direction of the magnetic field. You've seen variations of this problem. In other variations, the particle is moving in one direction or the other, and you have to figure out the direction of the current. But in this case, we first want to figure out the direction of the magnetic field. Thumb in the direction of the current. Fingers go into the page and then out of the page. So I draw that into the page on this side, out of the page on this side. So now all I'm concerned about is this portion where I have a velocity vector that's down and a magnetic field vector that's out of the page. And so now this comes back to our first application of the right-hand rule. V is down, V is out of the page, and so my force is going to be, what was that, to the left? Yeah. So this particle is going to initially feel a force in this direction, and so it's going to follow a path that will look like that. That force is going to pull this particle over, so it moves in that kind of circular path. Now, just a second, Mallory. The force actually changes with time, right? The force comes here, and then it comes here, and then it will continue in a circular path. But initially, the force is to the left. Mallory?
I can't think of any question like on the exams I've seen like the example, but like, are we gonna have any that you say like what direction is the particle gonna go in?
Yeah,
Oh,
probably.
or how do we tell that?
Okay.
Besides like the right handle, like something
Nothing different. What do you mean, something
I don't
different?
know, like in other tests like we have those where something's going through a wire or whatever, like we have something like that where we say, this is your charge, where it's gonna go. Is there anything about the like you know, like do we need to know? I know that's a really that sounds so wrong
No, it doesn't
and
sound that.
confusing. I just wanna make sure besides the right handle, like we don't need to know where to get like where we're going.
Let's just look at some other questions.
Yes.
Okay.
I have a question. So if it asks you what direction, you always look for the force, right?
Yes. So direction is code for force. Because the force only changes the direction, right? Because it's a centripetal force. It only changes the direction. Doesn't change the energy, because it can't make it go faster or slower. Doesn't change the speed. It can change the velocity, right? Because velocity is a vector, and direction is part of velocity. But it doesn't change the speed. It can change the momentum. That's a vector. It can change, what else can it change? It only changes the direction of the velocity, not the magnitude. Let me open up that big file that I had sent y'all earlier. With all the right-hand rule stuff in it.
So something changes the direction of velocity, but not in magnitude. It'll just be like negative 5 or positive 5. Like that would be a change. You can't go from 5 to 4.
Right. The velocity does not change magnitude. This was that big file that I sent you guys. We used in help session. Yeah, so like these are the types of questions that you'll see. Like, for example, what is the direction of the particle that it experiences? Well, that's a lowball one. What is that one?
Up.
It's up, yeah. Were you doing this?
Oh, no, it's doing
Oh,
that.
she's doing the wrong one. V is here, and so it's going to be V is into the page. It's upwards. See, this one is to the left. Fingers in the direction of I, magnetic field to the left. Okay. Have we got on right hand rule? Yeah, Devlin. Uh-huh. Yeah, so it's just like what we did over here. Fingers in the direction of I, they fold towards the magnetic field, or you can think of the magnetic field coming out of your palm. That might help. And so the magnetic field comes out of my palm, and then my thumb gives the direction of the force. Sometimes this is hard to situate just right. I'll take my paper and reorient it so that it's easier with my fingers in the direction of V. Like turn your paper upside down if you need to. No?
54 is something I'm trying, that I was trying to find out. Like, I don't know.
Yes. So if my velocity vector is initially in this direction, if this were a positive particle, Q or V would be in that direction, the magnetic field is out of the page. If it were a positive particle, it would feel a downward force. But it doesn't experience a downward force. The force actually causes it to move in this direction. And so, since the force is opposite what I would think it would be for a positive particle, that means it must be a negative particle. Yes. Okay. Yeah, Christian.
52, the direction of the magnetic field is kind of opposite. So thought the Y is
Oh, yeah, you're right. That. This isn't the magnetic field that the wire generates. It's just, you think about this, say that this one, say, generates a really small magnetic field, but this one is really big. But you're right, that this does generate another magnetic field that is into the page on this side, out of the page on that side. That's a good point. Okay? Look back at that exam. It's good to look at this, but this is only a selection of problems. You're going to have to order your electromagnetic spectrum. You're going to have to do mass spectrometer. I think there might have been an OpenStax question on that too. You're going to have to figure out the magnetic field either for a solenoid or for a single wire. Make sure you can tell those two equations apart. Right, use the N. A solenoid has an N value, or it can have a single loop, but think of that, it has an N. All right, know your magnets. Light. Know the history of light, Newton, Einstein, Huygens, and Young, why they thought light was what it was. Know your mediums, you will have to do that. You'll have to rank your mediums based on speed or index of refraction. You'll have a question like this. You'll stop me. Yeah.
much like the angle of like change or the instrument's angle, like what angle is named y-axis? I don't know, like, if you just like drew,
I'm sorry, I just heard yes over here.
drew
Can you?
something with a bunch of angles and said, find the incidence angle.
Mm-hmm.
I'm like, okay, like,
Yeah, the incident angle, which we usually call theta 1 in the law of refraction, is the angle that's incident on the medium. And then the refracted angle, which we usually call theta 2, I'm going to write this down in a second, but theta 2, or the refracted angle, is the light ray that's refracted after it goes through the other medium. So if I'm looking at two light rays, one here and one here, this is theta 1. That's what we call it in the law of refraction. But it is also the incident angle, because it's incident on the medium. In fact, we call this theta I2 for incident angle, because it's the incident ray, the ray that first hits the surface. And then this is theta 2, and we call this the refracted ray. That's all.
so what if, sorry,
Oh, well, it doesn't matter. So it could be that way. Instead of going down, this is what you mean? It goes like this?
or it makes it be like this.
Oh, well, that would be reflection. If it's like this. This is my incident angle. And this is not refracted, it's reflected. Yeah. You're right. So let me repeat what she said. I think I understood what she said. That let's say that we had this, but in medium 3, instead of doing what it does there, my sync is not quite on. That it does something like that. The point being here that this ray and this ray are parallel. Isn't that what you were asking? If that's the case, this index is equal to this index. Remember, we can get rid of medium 2 completely and just imagine that it's not there. And if I have a light ray that moves from here to here without being refracted, without being bent, then these two media are the same. That's a good point.
Yeah, I'm in the angle, so if,
Yeah, then this angle would be the same as this angle. That theta 1 would equal theta 2.
so when you look at the angles, you have to draw the normal to know where to put it.
Yes, it's always to the normal.
So here, medium 2 has the base index.
Oh gosh, I don't know. I'll have to look. So you're going to have a question like this. I always have to go through the process. I imagine my wave fronts traveling through here. I know here it has to slow down, right? Because this is going to speed around. So then I know N2 is bigger than N1. Because light slows down when it enters medium 2. And then here, this speeds up. And so N2 is bigger than N3. So yeah, N2 is bigger than both N1 and N3, and so it's the biggest one. We could also figure out what is medium 1 to medium 3. Well, imagine this. It speeds up when it goes here. I'm trying to imagine that medium 2 doesn't exist at all. So it travels faster in medium 3. So which is bigger, N1 or N3? N1 is bigger than N3. So my order would be what? N2, N3, no, N2, N1, N3? Right. Yeah, medium 3 is the fastest. So if I was ordering my velocities, it would be V3, V1, V2. It travels slowest in medium 2. When the index is biggest, it travels the slowest. It's inversely related. Okay. You'll have all of those. For the light stuff, the mirrors, I want you to know what positive magnification means. That's upright. Know what negative magnification means. That's inverted. Know what positive Q means. That's a real image. And know what negative Q means. That's a virtual image. You also need to know that M is equal to negative Q over P. And you need to know what a flat mirror image looks like. It has a magnification equal to positive 1. That means that it is upright. It is the same size. This is going to blow you away. Because it's positive, it's always virtual. Why would a positive magnification imply a virtual image? You're right. So M is negative Q over P. If this is negative, then M has to be positive, because P is always positive. But if Q is negative, then M has to be positive, the magnification. So virtual images are always upright. You never see virtual images that are inverted. So unless you have a 2-lens or 2-mirror system, we'll get to that later. Okay. Okay. Yeah, Tristan. A real image can be projected onto a screen. A virtual image cannot. That's the only difference. So this is a real image, but if you look in your flat mirror, you can't project that onto a screen no matter what you do. It's a virtual image. These are all good questions.
Is there a mirror in there?
Is there a mirror in that? Probably not.
How? We don't have a projector on our mirror we look into, so how do we have to project that?
What?
Like, I don't understand that. Like, virtual image.
You can never take a flat mirror and project an image onto that screen. No.
Yeah, I know, but how? Because you don't have a projector.
What are you talking about?
Like, if you just have a mirror, of course you can't project it onto the wall.
But if you try to shine light onto a flat mirror, you would never project an image onto the wall. You would get diffuse light that would shine onto the wall, but you would never get a clear and sharp image.
Okay, project that image, like if the screen was in there and nothing shows. That's good light.
Yeah, it would show up if the screen was a mirror. It would show up as, I don't know what the heck would happen actually. Never thought of that. But you can't project a virtual image onto a screen.
Are we gonna have questions like this?
Yes, absolutely. I think you have about 4 questions that relate to this.
Like, what
Yeah,
about
4.
knowing that stuff or about this stuff we're talking about?
Yeah,
Why?
this stuff about.
Okay, just that. Not
This is what we're talking about.
It's
Okay.
easier like that.
You'll also see a ray tracing diagram. We went over those in class. A ray tracing diagram for a flat mirror. You remember how to look at those? Yes? So let me show you. Look. If I have an object right here, I can draw rays in a variety of ways, but I'm always going to draw them so that the incident and reflected angles are the same. And then the refracted ray, or the virtual rays, that's what these are called, virtual rays, will just trace back from the reflected rays. You want to always look for where the 2 virtual rays cross. That's where your image is going to be. I didn't really use a ruler here. This distance should be equal to this distance. And the image should always be exactly opposite the object. That's always true in flat mirrors. And the image is the same distance as the object distance, and it's always exactly opposite from the object. It's not off to the side. Doesn't matter where the observer is, it's all question of that. Okay? What else? Yeah, of course. Let me just make up one. You just need to remember your law of reflection, and you need to remember your triangles. Let's do one like this. Let's say this angle is about 40 degrees. And then I have a light ray that comes in. Let's say that I have it come in at 30 degrees. And I want to know, after this thing bounces off the second mirror, what is its reflected angle? So first, I draw this ray, and I know that this angle is 30 degrees, because for flat mirrors, theta I, the incident angle, equals the reflected angle. And so this angle is equal to 60, and that means that this angle is equal to 80 degrees. Because notice, this is a triangle, and a triangle has a sum of 180 degrees. Now, if that angle is 80 degrees, this isn't a very good example, but this angle has to be 90 minus 80, or 10 degrees. That means that the reflected ray will reflect also at 10 degrees. It's going to be a question practically identical to that, except this number will be different, and this number will be different, the 30 and the 40. But the process of working it out is always the same. The reflected ray is the same as the incident ray. This angle is 90 minus this angle, because this is a normal line, so this is a right angle right here. And then this angle is 180 minus the sum of these angles. 180 minus 100 is equal to 80. And then this angle is 90 minus this angle. Okay? Just remember your right angles and your triangles 180 degrees. And you will have one of these here as well. Okay. All right. What else? Anything else?
Are there any torque
Torque. Yeah, you know, like if you have a loop, what is the torque? They're not that hard, right? It's just a nibble. I forget. I really did forget. Okay? Is that all? All right. If y'all could hang out for 1 minute, I forgot to print out the roll, and it's a lot easier if I just have the roll on and check you off. So just hang out for 1 minute. Let me. Yeah, I got you.